Let's go. We have seen an example in which convergence in probability does not imply almost true convergence, and we saw the characterization theorem for convergence in probability, and one simple proposition, and then we saw the convergence metric for the metric for convergence in probability. Now, well, let's take a look again at the metric. We say that the distance between two random variables is defined as the expectation of the difference in absolute value between them. And with this, we can state the following proposition. Xn converges in probability to X if and only if the distance metrics, the distance metric between them, between this sequence of random variables and X goes to 0, as n goes to infinity, right? Yeah, n goes to infinity. Good. I don't know if we ever use this in practice, because I have never seen it in any of the exercises, but it was required in one of the theoretical questions. Now we have another theorem with the convergence, with the metric for the convergence, which says the following. Xn converges to X in probability if and only if the limit as n goes to infinity of this expectation right here, the difference in absolute value between Xn and X over 1 plus the difference goes to 0. And the proof is not very long. So, without loss of generality, fix X equals 0, and the claim becomes that Xn converges in probability to 0 if and only if the limit as n goes to infinity of this expectation X absolute value of Xn over 1 plus absolute value of Xn is 0. Right? Yes. Now suppose that Xn now since I don't know why it's written suppose here. So, since Xn converges in probability to 0, this means that for any epsilon greater than 0, we have that the limit of the probability, well, the limit for n going to infinity of the probability that Xn in absolute value is larger than epsilon, this limit is 0. And now, note or observe that absolute value of Xn over 1 plus absolute value of Xn is bounded above by the same quantity restricted for absolute value of xn larger than epsilon plus epsilon times the indicator on the values in which it is smaller. And this is basically I don't know why we have this absolute value of xn larger than epsilon plus epsilon, and then we have that the expectation of this quantity is bounded by the expectation of the indicator where xn is larger than epsilon plus epsilon, which is nothing but the probability that xn in absolute value is larger than epsilon plus epsilon, right? Now we take the limit and use the hypothesis that xn converges to 0 in probability. So we have this, the limit as n goes to infinity of the expectation for this thing is bounded by the limit of this thing here, but if xn converges in probability to 0, this probability goes to 0, and so we have epsilon, so this is bounded by epsilon. And since epsilon is chosen arbitrarily, this limit is 0. The limit as n goes to infinity and now observe that f of x plus x over or x divided by 1 plus x is increasing, and therefore epsilon plus 1 over 1 plus epsilon times the indicator where xn in absolute value is larger than epsilon, this is bounded above by xn in absolute value over 1 plus xn in absolute value times the indicator when it is larger than epsilon, but this is further bounded above by the quantity without the indicator. And now taking expectation and the limit for n going to infinity, we get that epsilon over 1 plus epsilon, limit over n going to infinity of the probability that xn in absolute value is larger than epsilon, is bounded by the limit for n going to infinity of the expectation that this thing is 0. And so, since epsilon is arbitrary, we have that the probability that xn in absolute value is larger than epsilon is 0 e punto. So, then let's try to dissect a little bit this proof. Here we have one remark that says that the proof refers to f of x of this form, but it actually holds for every bounded non-decreasing continuous function on R plus. So, what did we do here? We rephrased the statement to simplify calculations. Okay, so rephrase with x equals 0. Now, recall the definition of convergence in probability. And here what do? We bound the quantity of interest we take the expectation and the limit now. Why this is not here, I don't know. But in any case, we take expectation and limit and we find out that the limit of the expectation goes to 0. Then we consider some function which is we observe that the function is increasing, so that we have something strange with the epsilons. Okay, so we bound this thing here. To prove that it goes to 0. We bound probability that xn is larger than epsilon by expectation going to 0. Okay. Now let's see the definition of convergence in the LP sense. A sequence xn of real valued random variables is said to be to converge to a random variable x in LP. Well, let me write it in this way. X n converges in LP to X, if for any n xn is in LP, meaning that it is in the absolute value of xn at LP power is integrable, meaning that the integral is finite, x is in LP, and more importantly, the limit for n going to infinity of this expectation xn minus x at the p power is 0. So how does this notion differ from the previous ones? Here we consider the expected value, which is the mean. Basically we have this is an alternative way. Recall that the norm, the p norm of x is the expectation of the absolute value of x at the p power, all of this to the 1 over p, or in other words, the integral over omega of x at the p power dp all of this to the 1 over p. And basically the limit as n goes to infinity of the p norm of x n minus x is 0. This is equivalent. So for almost sure convergence, we look at the realizations, and the realizations converge to some numerical value. For convergence in probability, the probability of the realizations becoming closer and closer to some value increases, while for convergence in LP, the mean of the random variables becomes closer and closer to the mean of another random variable. And here we have a remark that says that if xn converges in LP to x, then x is unique up to equivalence. This because of the integral, basically. If you change some points, if you just change some points, the value of the integral doesn't change. And so even if you have two different random variables with some different points, with a finite number of different points, then the value of the integral is the same and you obtain the same expected value. And for the proof of this, we have that xn converges in LP to x. No, wait. This is simply a proof that it is up to equivalence. So now, one important remark is that convergence in LP implies convergence in probability. So if the mean of the sequence converges to the mean of some random variable, the probability that the sequence gets closer to some value increases. Okay. And the proof of this is a one line, basically. Using Markov, we have that this, which is a positive, I mean, it is a probability, so it is larger than 0, xn minus x larger than epsilon. This is bounded by 1 over epsilon at the p power times the expectation absolute value of xn minus x at the p power, which goes to 0 and goes to infinity. So this quantity is 0, and so this quantity is 0 by the squeeze theorem. And so they are equal. I do not understand the implication. However, convergence in LP does not imply convergence in probability, does not imply convergence in LP. We will take a look at a counterexample. Probability does not imply convergence in LP. So consider the following probability space omega HP with the classical interval, closed interval 0, 1, the Borel sigma algebra on it, and the Lebesgue measure. And consider Xn sequence of indicators of the intervals I don't know why we have the same interval here, but I mean 0, 1, it is basically the previous example. 0, 1 half, 1 half 1, zero 1/3, 1/3, 2/3, 2/3, 1, and so on. So we proved Xn converges to 0 in probability. And observe that Xn converges to 0 in L1. Why? Because the expectation of Xn in absolute value forms the sequence 1, 1 half, 1 half, 1/3, 1/3, 1/3, and so on. Now modify the sequence and consider this one, Xn hat. which is x1, 2x2, 2x3, 3x1, well, 3x4, 3x5, 3x6, and so on. Such that xi is this thing here. Xi hat is 1 over, it is xi times 1 over expectation of xi in absolute value. Why? Now evaluate the probability that xn hat is larger than epsilon. This thing is the expectation of xn, and taking the limit, xn hat converges to 0 in probability. However, the expectation of the absolute value of xn hat is 1 for any n, and hence xn hat does not converge in the L1 sense to 0. Okay. And as usual, we have another characterization theorem. This time for convergence in one. Let xn be a sequence of real valued random variables. We have that the following statements are equivalent. Xn converges to x in L1. Xn converges in probability to x and is uniformly integrable and lastly xn is Cauchy for the L1 convergence, which means that the limit for n going to infinity of the expectation of xn n of the absolute value of xn minus x is 0, right? Yes. For n and m. For n and m, and m for any m larger than m. And we have also a proposition. Xn converges in the L1 sense to x, to random variable x. If this happens, we have that the limit as n goes to infinity of the expectation of xn y, xn times y is the expectation of x times y. This for every bounded random variable y. And as an observation, we have that setting y equal 1 almost surely, what we get is that xn converges in L1 to x, implies that the limit as n goes to infinity of the expectation of xn is the expectation of x. Okay, so we have seen the notion, the definition of convergence in probability. We saw some results related to it, some examples, and then convergence in the LP sense, the characterization theorem for convergence in L1, and finally we can conclude the notions of convergence talking about weak convergence. Consider mu1, mu_n, a sequence of probability measures on R. This is said to converge weakly if, well, to some measure mu, if the limit for n going to infinity of mu n f, the integral of f with respect to the sequence of measures is the integral of f with the measure mu for any f, which is continuous and bounded. I think this is the notation. And now a sequence of random variables xn is said to converge weakly, to converge in distribution to a limiting random variable x if the distribution of the random variables in the sequence converges to the distribution of x. With distribution mu is the sequence if the distribution of the random variables in the sequence converges to the distribution of the limiting random variable in the weak sense. That is to say, if the limit for n going to infinity of the expectation of a function applied to x, n is the expectation of the function applied to x for any continuous unbounded function. And now we have some relationships that I will just mention. Weak convergence implies convergence in distribution. Convergence in LP implies convergence in distribution, and normal sure convergence implies convergence in distribution. Now my question is, doesn't also convergence in probability imply convergence in distribution? Convergence in distribution is the weakest notion of convergence and is basically useless, I think. And let's read what it says here. Having the same distribution is not very informative about the behavior of the random variable. So for example, if we have y, a standard normal random variable, and z, which is minus y, still a normal 0, 1. If you evaluate y of omega, taking some value a, this is different from z of omega, which is minus a. Now we have one theorem that is important and relates convergence in distribution to almost sure convergence, and I think we will close with this. If a sequence of measures mu n is such that mu n converges weakly to some measure mu, this is equivalent to the existence of a probability space omega prime, h prime, p prime, and of some random variables y1, yn on it, such that the distribution of yi is mu I for any I from 1 to n, and the distribution of y, well, and there is some y with distribution mu such that yn converges to y almost surely on this space. I don't really know how we use this, but it says it's important, and it may be that we use it when we construct probability spaces involving to model stochastic processes, maybe. Okay, we finished page 4 of the notes. I basically forgot most of the stuff that we did, but at least we are trying. Let's take a look at what follows. The next session is a quite tedious one, which is about laws of large numbers and central limit theorems. Okay, for now I think it's enough.